Hello, everyone, and welcome to the Hyperthesis podcast. We're happy that you could join us for, I believe it's our 13th episode now, with a lot of interesting topics. But before we begin, I'll introduce myself and say hi, I'm Patrick.
I'm Feely.
And I'm Liam.
And this is the Hyperthesis. So before we get really into our main topic, we have a couple just sort of little topics that we'd like to talk about, just things that we've learned that are new to us or that are new in the news. So to start out, I believe that Liam has some interesting things about Steam.
I don't have a very quantitative description of Steam prepared. However, I'm in Ottawa right now at my girlfriend's place, and they have this teapot, this kettle, and you boil water in it and it makes a high-pitched noise. So I thought about it and said, that'd be an interesting thing to look into. So I looked up the physics of teapots or kettles and the whistling noise they make. So a teapot or a kettle is some kind of device that you use to bring water to a boil, where you use the boiling water to make tea or coffee or whatever. You can use it for cooking. So you take this thing, usually it's made of metal, fill it with water, you put it on a hot element like a stove or a burner, for example. After a while, the water heats up, comes to a boil at around 100 degrees Celsius. And when it does this, the pot produces a high-pitched whistling noise to kind of let you know that it's done. And you see this in movies and TV shows a lot. Usually when people are stressed out, it makes this high-pitched noise. Fun fact, Harry Bramston, the inventor of the whistling tea kettle. I have no idea who that is, but that's what the internet told me, so I have to believe it no matter what. So I was basically interested in what makes this noise. So once the water gets to its boiling point, you know that it begins evaporating from its liquid form into its gaseous form, so steam, and it's produced within the pot. So there's this hole in the kettle that's always there, and the steam can escape from it, even when the water's not boiling yet. However, once it begins boiling, the pressure inside the pot becomes powerful enough that it shoots the air out of this hole at a high speed, and it's the vibration this air has against the hole which causes the noise. It's actually kind of just like a whistle, like a tin whistle, or like a recorder that you might have learned in school. Other types of instruments, like their whistles, are like flutes, piccolos, pipe organs. It's just a type of whistle, it turns out. So it's a fluid mechanics problem. And by understanding the geometry, the dimensions, the properties of the fluid, which in this case is air and steam, you can predict this noise. And it turns out it's called a hole tone. So this noise that the kettle makes as the steam shoots out of the hole. And it turns out that, well, maybe not every kettle or pot, but, a good example of a kettle is almost a perfect hole tone. And by hole, I mean HOLE, not WHOLE, to clarify. And what I thought was particularly interesting about this was that this is a very well-known thing. Kettles have been around for quite a while. But interestingly enough, this phenomenon was not actually understood fully until 2013, when a paper called The Aeroacoustics of a Steam Kettle, was published by a fourth-year engineering undergrad and a supervisor. So I thought that was pretty neat. And I find that happens a lot in physics, actually. You have these super well-known things that happen, and it's not until many, many years later that people look into it. Like, people have a rough understanding of what's going on, but they don't get into the kind of fine mathematical details until later in time.
That's really fascinating, and a couple of questions come to mind. Like, what exactly, I guess, is the big difference between this type of hole whistle and something like a flute, where you have partial air passing over, say, a hole and part of it going in, or like a pipe organ where you have very obvious openings within the actual instrument itself, whereas it's just a single hole with steam being forced into it. I've never really thought about that, so that's very interesting to think about the difference and why exactly they are different.
Yeah, and I think it reminds me of when you blow into an empty jug or a bottle and it makes a noise, like a "whoo" noise. But I think that's different because it's not when I think of a whistle, I think of air going in one end and coming out the other, where the bottle, it goes in one and comes out the same end. So, I'm not sure of the exact differences, but it depends on it's a fluid dynamics problem, so it depends on your Reynolds number, which is basically just kind of the ratio of how viscous some fluid is compared to how fast it's moving. It depends on what your fluid's made out of, um, how big the hole is, kind of resonant stuff, but yeah, I don't quite know. However, from a quick look online, if you just Google, whole tone or, like, the kettle whistling effect or something like that, there's an entire very in-depth Wikipedia page on, whistles, and it goes into kind of, like, all these different instruments and the different types of kind of whistling you can have, and I think it explains the differences between them all.
Interesting. I know we did an episode on sound previously, so go check that out. But yeah, it might be interesting to maybe delve deep into the physics of different instruments, like a trumpet versus a pipe organ versus a tin whistle, and all these different instruments, just to see what are the differences and really dive deep into that.
Yeah, that's something I wanna do too, because the episode on sound we did, I could talk about sound all day, um, and I don't there's a lot I don't know about it still, but I'm extremely interested in it. Like, I just think we talked about this in our previous episode, but I think it's very interesting how you can have different types of sound, but with the same frequency, um, and stuff like that. So yeah, we should definitely do an episode where we talk about different types of instruments. Maybe we could have a few episodes where one's on stringed instruments, one's on whistles, blah blah blah.
Agreed. So as a bonus topic, if no one else has any other comments, something that I learned that's really fascinating from this past week is exactly how electric eels zap. So, similar to kettles whistling, electric eels are kind of in the public mindset of, oh, they do this thing, but it's not as common for people to ask, oh, well, why do they do this thing? So, electric eels, which are commonly found in the Amazon River and within the rainforest area, are aquatic fish technically. They aren't eels, they're more closely related to catfish, but they have a dedicated organ that's able to produce electricity. And when I say produce electricity, it's not like, oh yeah, it's just like creating some sort of static electricity and discharging it. Instead, it's actually creating a potential across the length of a specific electricity producing organ and then firing that intentionally based on signals to those electric producing cells.
So in movies and TV and things, when I see electric eels electrocute things, you see all these like lightning bolts come out of it, and it's like and it makes like the electricy noise. But I imagine that doesn't actually happen. I imagine it's more like if you accidentally touch something with a high voltage, and you just kind of stiffen up, and it makes like a very sudden zappy noise, and you go ah.
Well, I imagine if you had like a very dark room and maybe a very well exposed sensor, like a camera, then you might actually be able to see it because they're in salt water. So they're in the part of the Amazon that's a little bit saltier than just natural fresh water. And so you would think that you might be able to see some sort of evidence of these shocks. But the thing with these shocks is that they last only, I think it's just a couple to a few milliseconds. But the interesting thing about how they produce them is one, they can control how much charge essentially they can dispel at once. And then they can also use those different, essentially, levels of electric shock to do different things. So the electric shock itself is created within cells within their specialized organs. And now these cells, each one they're able to produce a potential across them. So one side is slightly positive, one side is slightly negative, and there's a whole bunch of these cells in series. So for anyone that's taken really any electronics course or has worked with batteries in any real case whatsoever, you'll know that as you add up batteries together, they create a higher voltage. And so these cells that create just a little bit of a potential across them, there's many of them stacked together, and they're actually acting exactly like a battery, where each one has a small little potential, and then they're able to create this overall massive potential. Like, I'm talking, I believe it's over 1,000 volts kind of thing, and up to 1 amp.
Well, yeah, I think it was like around 800 volts or something. But I think, their cells are connected in series, right? If you want to add up the voltage, because, if you add it in parallel, you're going to have the same voltage as one battery, but maybe you get more amperage out of it. Yeah, but it's interesting how kind of the evolution side come out. Like, what makes this is the strange randomization that doesn't happen in like land animals. You don't see electric zapping bird or something. They might exist somewhere. Who knows? It's such a kind of the randomized process of nature is kind of weird.
Well, air is not very conductive, right? And I don't know anything about biology. I don't know how over millions or billions of years, well, maybe not billions, but thousands and millions of years, how an animal somehow develops a battery within itself that it can discharge to keep, predators off of it. But I can understand that it's a sea animal opposed to a land or an air animal, because the air is a very low conductance, whereas water is definitely a lot more conducting.
Especially salt water.
Yeah.
And there are actually a few different species that are not these electric eels that also produce electricity, but electric eels are by far the most potent in their voltage. And speaking of evolutionary terms, it's interesting. The main theory right now is that these essentially little battery cells inside of them are specialized muscle cells. Because if you think like when you get an EKG or an ECG where they measure your heart rhythm, that's all electrical impulses. And so when you flex a muscle, that's coming with some sort of little electric current to actually get your muscle to move. And so just specialize that a little bit, and then you get this dedicated organ which is able to produce a giant zap.
Well, when I learned about taxonomy, I think one term they use is fitness, right? For evolution and stuff, what type of traits contribute more to the survival of the species. And electricity is to me, it's just a great tool. Like, you can kill a large animal with electricity easily, right? Like, I'm surprised it's not evolved more in land. Imagine like you have a snake and you just like, cling onto you and shock you to death. That's terrifying. I'm surprised it's not a big thing. Maybe the stochastic process wasn't exactly, lucky this time.
Yeah, it's very interesting that we don't have more, given the number of species that we have on Earth, that there aren't more electrical ones. But having a snake shock you to death would be terrifying.
It might be that people who got in touch with those species just never get to live to tell the tale, because you just never get out. Nevertheless, I feel like to move on a little bit to our main topic. So we had nice story, little news on the electric eels, and a bit about the pot calling kettle whistling. Anyways, so our main topic today is gonna be about the optics and eyes and how we visually perceive the world. And there's a lot into eyes and the physics of it, and also the biology of it, the anatomy of it. But eyes one of the most complex organs in our body, be able to collect these light and photons. And I think our brain interprets it really well, right? But I feel like, it's just crazy how we can perceive things to this fine details of the world around us. So I think Liam got a big topic on this.
Well, I am by no means an expert. Um, so we did an episode where we talked about sound, like we said, and we talked about the human ear a little bit. So I figured it'd be fun to talk about the eye. And again, the eye is a very complicated thing. And I'm gonna kind of give you a theoretical physicist point of view. So it's gonna be very simplified. Um, so yeah, sight is a very important sense. You know, I don't know about you, but I use it a lot, and not being able to see can make your life a lot more difficult in a world where many things are based on seeing. So what is seeing? We see things with our eyes. You know, I'm looking at my laptop right now. I can see that it has letters on it. I can see light coming out of it. Um, so light is just, well, it's a particle and a wave, and we should probably have another episode about that, but I'm not going to get into it. Basically, it's electromagnetic waves, or photons, and they're emitted from the sun in huge amounts, or from light bulbs, or even from bioluminescence. There's different ways to get photons, but the sun is kind of the main source the Earth has, and emits just this huge amount of light, and a lot of it fires off into space, but a small amount of it hits the Earth. And it hits an object, so say like a car, you know, you're standing on the side of the road and you see a car. All this sunlight comes down, it hits the car and it bounces off in all these different directions, and some of that enters your eyeball. And that's how you see a car. You see reflecting light off of things. It enters your eyes kind of turn that signal into something that goes to your brain, and then your brain gives you an image.
Well, there's one heck of a detour to get into a sight from the sun, from the stars. Yeah, but basically just light in hitting the cells that the purpose of those cells are to interpret or change from light to electricity, basically, right? Like I remember from my biology class, the cone cells in your eyes are responsible for the color and whatnot, and they can get tired and stuff, right? So imagine if you look at the room with red light, and your red cells would be so tired. You walk out, you can see less red, and to me, that's just literally is a organic photoelectric effect. Basically, just convert photons or light into electricity or some kind of voltage or current that our brain can process.
Yeah, that's exactly it. And I don't know that exact mechanism. That's actually a good question, and I want to know. I didn't look into that. I just kind of skip the biology and chemistry details a bit just because I'm not that great at chemistry and biology. But yeah, so when you see something, that's exactly it. Light's hitting your eye, it's going, and I'll get into some of the parts of the eye in a minute. Um, but we see things in color, or some people do, some people don't. And what that is that um, basically what you see is determined by the frequency of the light that enters your eyes. So there's all different kinds of frequencies of light, many different kinds. But we can't see all of them. So, for example, infrared light and ultraviolet light are two kinds that we can't see. And it just depends on its wavelength or frequency. So we can only see light that has around a 400 to 700 nanometer wavelength. So that's pretty small. 400 being kind of violet and 700 nanometers being red light. And when we see a color, oh, sorry, I should mention that 400 to 700 is kind of the visible spectrum. It's the rainbow. Anything outside of it is some other color that we can't see or perceive. You know, it's like it's trying to imagine like what a fourth dimension looks like. Well, we can't really do it because we live in 3 dimensions. It's like, well, what is the color of infrared? Well, we don't know. So we can use a different camera that sees infrared light and we can assign it some other color.
Just to add in, it's interesting to see images that are taken in infrared or ultraviolet or even X-ray because false color has to be added to them so we can actually interpret them. So going back to a previous episode with the James Webb Space Telescope, any image you see from there is infrared, but it was given false color so that we can better understand it.
Exactly. And it's even like you see well, I always think the kind of like Call of Duty, like war video games. You see these infrared cameras that you're looking through scopes at people with, and they're glowing like bright red or bright white. It's because the human body is constantly emitting infrared radiation. We can't see it because we don't see people glow all the time. So you can use a camera and you can assign kind of a visible color. The camera can detect those frequencies of light, and then we kind of give it a color so that we can visualize it.
Yeah, and the resolution of the eye is crazy because if you think about the camera, right, it needs like a large sensor for pretty high resolution. Our eyes around like 576 million pixels, and that's a lot. You think of your iPhone or smartphone camera, the top tier one probably around 20 mil at most, 20 million pixels are not they're not doing that great either. And like professional cameras can go up to 10, 15, or even 40 million pixels. And like the medium format is one of the largest one. So it'd be like a large sensor, like 6 by 9 centimeters wide of the sensor size. Around like, can get only around 120 million pixels. And that's a lot when you use for photography and stuff. But it's nowhere near like the eye, the small sensor, the eye have like 4 or 5 more times resolution. Is to me that's insane.
Yeah, the eye is an extremely interesting organ, and what's really cool about it is that if you take like a camera, that you're taking pictures at a wedding with apart, many of the kind of components in the camera are kind of the same in your eye. Like it has a lens, your eye has a lens, and I'll talk about that in a minute. But it's really cool, and what's in I citation need it for this, but I remember my old supervisor was talking to me about the human eye and how it's so sensitive that it can detect a single photon in complete darkness. And that kind of blew my mind because a single photon is a very, very, very low energy thing. A photon within the visible spectrum. So if you're in a completely dark room, you fire a single particle of light into someone's eye, they'll notice it. And that kind of blew my mind.
Yeah, and also the eyes biologically, in terms of evolution, it was made to for sight underwater. It's not for air. Like historically, I think because mammals were in the water, I think most animals were in the water before, right? So the eyes were evolved to be able to see underwater. That's why like we have liquids in our eyes, and when we get up onto land and through millions of years, we will still retain that water. But when you think like it's not pure water, that liquid in our eyes. But to think about it is it's fascinating how our brain has to reinterpret that to have these nice ratio and perspective because the light would get refracted before it gets into our retina, which is basically the sensor. And and that's gonna skew our perception a bit, but our brain is so used to it. Like what is straight line, but the light is going in. Because if you think of camera, it just go to the lens and air and lens and air and then sensor. But our eyes go to the lens and go to liquid and to the retina.
Yeah, so maybe I should describe kind of the basic kind of parts of the eye. But before I do that, let me finish up my kind of what is color. So color is basically just the wavelength of light, and white light consists of all the colors. Essentially, consists of every wavelength of the visible spectrum. And the sun doesn't emit pure white light; it emits basically pure white light. But there's tiny little bits of it missing, but it's white enough. So if I look at a car and white light hits it, so when the sun emits white light and it comes hits the earth by chance and reflects off of it into my eye, whatever material that car is made out of, it'll absorb some of the light and reflect some of it. Nothing's a perfect absorber and nothing's perfect at reflecting. So if I see a red car, that means it primarily absorbed every color in the visible spectrum besides red light, and the red light was primarily the one that bounced off of it. So what you're seeing through an object is the light it reflects. And that's why the sky is blue, is because it's blue and it's red at sunset, but that's another discussion. But it's blue basically because it scatters blue light off of it more than it does the other colors, and that's what hits your eye.
Yeah, and that's why people like wearing white in a hot day because it reflects all the all the lights, right? And you're wearing black, like you're hotter. It's it actually get you warmer too. Like, yeah, that's the fascinating thing about color when you think it's a little bit counterintuitive because you think, oh, there's a property of the thing, this is red, but it's actually is a color that it doesn't want. The object doesn't want that color, so it spit it out for our eyes to see.
Yeah, I remember thinking about that at one point, saying like, "Oh, if the car is red, that means it absorbs every color except red." So it's not red in a way, but it is because that's what it's reflecting. So how does an eye work? Again, it's quite complicated. So this is my kind of simplified version of it. So your eye, or just one eyeball, say it's this roughly spherical thing, and it's filled with different liquids and components. But the kind of one of the main components is the aperture. So this kind of controls how much light enters your eye, and that's essentially your pupil. So the pupil is this hole that leads to the inside of the eye. So when it's really bright out, your pupils shrink to let less light in, so they don't kind of damage your retina. Which is the retina. I'll get to that in a second, but that's what absorbs the light and sends a signal to your brain. When it's dark out, your pupils expand and they let more light in, so you can see better at night.
So just to clarify, it's the iris that does the expanding and the shrinking.
Yeah.
And so the iris is like the actual aperture, and then the pupil is the resulting hole. So the iris itself is like a muscle that expands and contracts, and that's a
Mhm.
pretty color part of your eye.
Yeah. Sorry. Yeah, that's a better explanation. So why is the iris colored? Is there a reason? I don't know.
It's similar to like melanin in your skin. It's just some pigmentation, but if you have blue eyes, then you don't have pigment.
Yeah, it's just basically just genetic mutation, right? And I think it people didn't have blue eyes until a few, I think, million years ago, where it was like like an anomaly that became passed on a lot. If you see like Asia, we don't have light color eyes much, right? Because I think that's pretty rare. It just happened in certain part of the world, and then it just spread out a little.
Okay. So yeah, there's the iris, the aperture, and then the pupil is the hole that leaves, which lets light in. And that muscles kind of the iris, the muscles kind of contract and expand it depending on how much light wants to get in. And I'm skipping some components, like there's some. I'm skipping a lot, but these are kind of the important bits as far as I'm concerned. Um, so behind the pupil, there's a lens, and it acts like you'd think. It's kind of like any lens in physics. So light enters it, it focuses it, and that lets you see things clearly, assuming your eyes work. Um, and it's like a magnifying glass, right? Like you see on TV and stuff, or maybe you've seen in person. If you hold a magnifying glass in the hot sun, it will focus the light onto a point, and you can burn ants and stuff, which is kind of cruel, but it's similar idea. It just takes light and focuses it.
Just another cool thing about the lens is it's very much like a magnifying glass, but if the magnifying glass were slightly flexible, because you have muscles in your eye that can actually control and slightly distort the shape of the lens so that when you say look from close, an object close to you to far away, that's actually your lens slightly adjusting so you can change your focus. And the reason why that gets more difficult as you get older is that starts to harden more and becomes less flexible.
Yeah, that's exactly it. So at the back of your eye, you have this thin layer of cells, and it's really thin. I think it's like roughly 3 cells thick or something, called the retina. And that's what the lens is focusing the light to. The retina is what collects the signal and transfers it to your brain. The light hits it, you see something, and then it produces that image in your head. So the lens, exactly, that's exactly it, Patrick. It focuses the light to the retina, and that's why I can read something right in front of me, but I can also read like a road sign down the street. It's because the muscles can bend the lens very slightly, and it can refocus things. So for example, like if you're kind of zoned out looking at a book, it might get a little blurry, but then you kind of snap back into it, your muscles flex a little bit and things come back into focus.
I should just add another interesting thing about the lens within your eye is that it actually flips the image. So the image that you see, say just looking straight ahead on the horizon, is upright. But in reality, that image is flipped and your brain is flipping it back so it makes sense according to gravity, essentially.
And your eye does all these other really interesting tricks too. Like, I think the veins in it, technically the light passes through a bunch of veins in your eyes to hit the retina, but your brain kind of manually cancels those veins out, I believe. And there's some other things too, like there's optical illusions where if you're looking at something, your brain will fill in the image or it will automatically do things. It's very interesting.
Well, I think we have to skip a lot of stuff because there's literally a field called ophthalmology, which you have to spend 4 years after standard med school study just about the eyes. And to me, that's a lot. There's a lot of years just for a little part, but so many muscles and whatnot. And the thing about that too is, we were talking about focusing and defocusing of light there, right? And like be able to focus, it's just a crazy thing that you can do too. Like it changed how things are perceived, right? And I heard that when you're a baby, I think less than 1 year old, you still see the world upside down because the brain hasn't realized that the world is upside down. So the babies had to learn. I don't know how they prove this in the medical way that they can prove the baby see upside down. I'm not sure if that's proven. Maybe it's not. It's not. Maybe just a conjecture. But it's it's believable. I believe it.
Yeah, I can see that. Babies stumble around a lot. They don't really know which way's up and which way's down. But yeah, citation needed for sure. But moving on so that we stay on track. Um, where was I? Oh yeah, so the retina, the back of your eye, that's what your lens is focusing things to, and it makes these very minute, very very minute changes to keep things in focus depending on how far away you're looking at. And like Feely said earlier, there's these different kinds of cells that make up the retina, and they're primarily these things called cones and rods. So cones are kind of responsible for the bright light processing. And again, I'm skipping over a bajillion details, but that's fine. We're hand waving is my favorite thing to do. Um, so during the daytime, your cones are kind of more responsible for what you see, and they're good at processing color. So when the sun's out, you see lots of color. Green trees, like red cars, whatever. However, at nighttime, rods, the cells in the retina, are better for kind of these darker, dimmer light situations. So as your pupil gets bigger, the rods kind of take over at night, and they don't process color near as well. So that's why when it's dark out, even if the sun's not up, there's still light from various sources like street lights or the moon or kind of like light diffusing through the atmosphere. There's still light, but it's just very hard for the human eye to detect it. So these rods can detect some of it, but their color processing's bad. So everything kind of looks black and grayish.
Yeah, but not all cones are made equal though, because that's why night vision visually is represented as green because it's easier to see from the eyes, right? And yeah, there are a lot of finicky things with it because when you're in a really dark room, you be able to see a bit, but you won't see color. You see this noisy black and white picture that it's kind of weird, but since it's part of human experience, we just think it's normal. But when you think about it, it's just kind of strange. Like, why are we seeing black and white in a darker room while the colors are kind of the intrinsic property of those materials, but we just weren't able to see it because the fault in our organs, basically, like the limitation of the sensitivity, which I'm surprised not solved. I'm sure for nocturnal animals or predators that need to be able to see well, they might even be able to see full color at night.
Yeah, I know there's whole bunch of different animals that have much better night vision than we do because their eyes at nighttime are more sensitive to the light. And I'm not sure about the color, but yeah, exactly. I'm sure there are some that can see color at night. And that's another thing. A lot of animals, they can't see a lot of colors. So when you think of like a tiger, like an orange and black striped tiger, I was watching a documentary and they asked like, why is it that in like a green jungle there's this orange and black tiger? And I was like, oh yeah, that's a good question. And it turns out a lot of the kind of gazelle or antelope or whatever, I might have said the wrong animal, but the deer-like creatures they're hunting can't see orange, and orange appears to them as green. So these black and white stripes blend in perfectly with their environment for their kind of the prey they're after, and it's all like this evolution and adaptation. It's very cool.
I will just shout out there is a fascinating documentary series narrated by David Attenborough called Life in Color.
Yeah.
So actually, they use modified cameras to show how different animals see. And so, for example, the deer not seeing the tiger stripes. And there's plenty of other fantastic examples.
Yeah, I think that's the exact documentary that's from, right? And there's also this, I won't get into it, but just a quick note, there's also this really cool creature called a mantis shrimp, and those things have wild eyes. They're like chameleon eyes. They move separately, they can process different things at the same time. They can see a ton more than we can, and their eyes can even see polarization, which is wild. But I won't get into that now. So eyes aren't perfect. All three of us here wear glasses for a reason, and many other people do. There can be a lot of problems with them. They're very complicated. They're very sensitive, so slight kind of discrepancies will cause problems.
Yeah, well, the color we see are a kind of, I don't know how standardized it is. Like, is the green I see the same way, the same green that you see? This, the age-old question, right? There was research that, women see more colors, that's why they're more sensitive to little change, minute change in color. And if you think of photography, like, all the phones you use, the photos you see are processed in a way that makes more sense. But if you do take like a raw data from the sensor, what people do when you do more advanced photography, you have to basically recolor it by yourself. Like you may use like what they call LUT, lookup table, to process different type of signal into different color. That's why some camera have different tones when you actually go shopping for cameras and such. Like Nikon has certain tone, Sony has one, Canon has one, and you have to pick what you like. And it's not might not be the most scientifically accurate, but to me there's no fault of the camera. It's by design. Each lens change the color a little bit, so yeah, everything is very sensitive to minute change.
Yeah, exactly. It's this question that we might never have a good answer to, but if every eye is slightly different, then presumably we all see colors slightly differently. Even if it's not by much, on some level it would be. So my green might not be your green, but that's a tough one because there's no good way to kind of physically see how one eyeball processes a certain wavelength compared to another. At least none that I know of. But to keep things moving, eyeballs have slight differences, and sometimes they're bad. So if you need to wear glasses to see something, odds are there's a problem with your eye, even if it's a tiny problem. Um, so, for example, nearsightedness or farsightedness are kind of things that you need to wear glasses. So, nearsightedness or myopia is basically you can see objects close to yourself pretty clearly, but objects far away are blurry. And it's just a physical thing. It's not your brain processing it. It's the fact that the lens in your eye is bad at focusing the light on your retina. It actually focuses um, the light to be too far ahead of the retina. So if you think of kind of the eye as a kind of a sphere or a circle, light comes in one end, and on the back of the circle, there's this layer of cells, the retina, and the lens will focus it, but it won't focus it on the retina. It'll focus it somewhere in the middle of your eye, roughly. Maybe not the direct middle. That's an over statement, but somewhere in front of the retina, and that will cause nearsightedness. So things far away, the light focuses too far ahead, and instead of getting this focal point on your retina, you kind of get this focal region, and the image becomes smeared or blurry.
I think you explained in a quite complicated way. To me, when I remember these in school, it was called short-sightedness because the light was focused too short of the retina, so it's short. It couldn't reach the retina, right? That's why the glasses we wear as for treating myopia is a concave lens, so it actually disperse the light. So instead it focus shorter, it makes the focus longer. So it actually focus on the retina. And if you think of long-sightedness, it's just the opposite. It's too long. The focus is too long.
Yeah, it's behind your
Yeah.
retina.
So it's interesting with nearsightedness, especially where your eyeball is just a little bit too long and your light's focusing is not quite on your retina. And there's a growing number of people with nearsightedness. And the main theory behind that is people aren't getting outside enough because bright light will trigger a certain hormone or some sort of chemical within your body to stop your eyeball growing, but only if you get enough bright light. So if you don't get enough bright light, then that hormone isn't produced as much and your eye keeps elongating a bit. So there is definitely an increasing number of people who are nearsighted.
Yeah, I can believe that. Like, even during COVID, there was like 2 years straight where I barely went outside. And every time I did, I was inside, my eyes were always focused at short range. There wasn't as much light. And the moment I go outside, it just felt like I had to struggle a lot more than I ever did in my life to see things far away. I had to like tense my eyes and squint. And thankfully, that's not happening anymore. But I can believe that.
I don't think that's your evolution growth problem though. That's just being in a dark place for a long time. I think that's more about. I think that's when you actually grow up. It's it kind of makes some sense though, because if you look at the world population, right, people who have smaller eyes are from places with a lot more sun. Like in Asia, we have I think my eyeballs, like my own eyeballs, I think are bigger than average. Maybe because they live in the dark. I don't live in the dark. I don't know why, but yeah, I think that's the thing.
Well, I guess I'm not really thinking of it like genetically. I'm thinking of like muscle usage, as in I'm inside for 2 years straight, and the muscles in my eyes don't look very far near as much. So when I have to, the muscles are kind of like, I haven't exercised in a long time, so they struggle a little bit. But yeah, and that's why we wear glasses anyway. Is that if you're nearsighted, short-sighted, there's other conditions you can wear glasses to fix. It basically just corrects the light that's coming in so that it moves the focal point closer to your retina, so you can see things better.
Yes, I think that's also why they tell kids not to stare at the screen for too long, too, right? Because you just use the focus just on this one length, and you're not exercising that muscle, or not even exercising. You overuse the muscle for that range. You're basically abusing too much, right? If you stare at the screen all day, like you get tired just looking something close, right? Like sometimes you need to stare far away to basically almost like use all the muscle or relax the muscle for the focusing. If you play video games or look at the screen all day, like it's very tiring.
And there's other kinds of problems you can have with an eye. A very common one's an astigmatism, and it's different from near and far sightedness in the sense that the eye itself has kind of these the lens will have distortions in it, and instead of focusing things to a single point or like kind of a region, it'll give you different focal points depending on where you're looking and how you're looking. So glasses can't correct that very well. So people with astigmatisms, everything's kind of blurry to them no matter if they wear glasses that correct nearsightedness or farsightedness. It has to do with imperfections in the curvature of the lens or the rest of the eye.
That's untrue. Actually, the glasses work with astigmatism really well. Like my glasses fix my astigmatism really well. I don't know what you're talking about. Like yes, but it's imperfection from the lens, right? Because the lens is supposed to be like, if you look at any of the pictures, drawings of an eye anatomy, they draw the lens like nice and smooth. But that's not always the case, right? They have imperfections and whatnot. That's why I think like LASIK surgeries go in and burn all those away with lasers. But the lens doesn't just do concave or convex, right? There are other things you can make a lens that correct those parts. But at the end of the day, what makes those have multiple focal point? You can just make an inverse of that into the lens, and I don't see why you can't fix it.
Well, the problem is that some astigmatisms are quite easily fixed by glasses, but some of them are very extreme, and no matter what you do, you can't get the to be perfect or even close to perfect. And I don't know the details of that, but some astigmatisms, like depending on if you look one way, things are blurry. If you look up, they're less blurry. If you look down, if you look far, if you look close, a lot of them are very mild and quite easily fixed by glasses, but some of them are extreme, and you have to do kind of what you just said. You have to kind of shape the lens to be better to fix it, or some other part of the eye.
So I guess in summary, the eye is quite the complicated mechanism, and it's amazing itself that we have eyes. I mean, the I guess the evolutionary tale of the eyes is quite extensive, and also the fact that not only have we evolved eyes, but other animals have evolved eyes completely separate. So convergent evolution, it's called. But I think with that, we'll have to wrap up the topic unless there are final questions or comments.
Well, I have one last thing that the fallacy used to believe. I used to think that contact lens have make you have a better, clearer vision, but it's actually untrue. I actually talked about optometrists about it. It's like, well, glasses are custom made to your prescriptions. Of course, gonna have a better, clearer vision, right? And I was like, yeah, I tried contact lens, but because my vision is really, it's pretty bad. So it's like, well, yeah, so true. I thought because it was closer, just on your eyes, should be better. Apparently not. Glasses are actually pretty amazing.
Well, with that, if you need glasses, go get them. Hopefully your insurance covers it. If not, there are budget options. And yeah, the eyes are pretty cool. So before we get on to our story, I'll just tell you about ways in which you can contact us. We are on so many different podcast platforms now, including Apple Podcasts, Google Podcasts, and Spotify. Our home base is anchor.fm/hyperthesis, where you can find a lot of our material and some notes about the episode. On Apple Podcasts, Google Podcasts, or wherever you get your podcasts, feel free to leave a review and let us know if you want to hear about a certain topic. Also, if you want to contact us, you can send us an email. We are hyperthesispodcast@gmail.com. We can also be found on Instagram at the Hyperthesis, where we'll post random photos. We do have a couple memes on there, and we'll let you know when episodes are coming up. But follow us on different podcast feeds, and if you're interested in either hearing a discussion about a topic that you like, or if you would like to be on the show, please send us a message either through Instagram or Gmail. And now, a story from Liam.
So this story, optical related, not necessarily, well, kind of eyeball related, but I'll get to that. It's about a type of lens called a Fresnel lens, and the story of a physicist slash engineer named Augustin Fresnel. So Fresnel was a French engineer and physicist, and his research in optics helped change physics as we know it, helped lead to the wave theory of light. And he also is kind of, again, most famous for this lens he created called a Fresnel lens, which is still in use today. And it saved many lives during his time. So his story, Augustin was a sickly child born in Normandy, France, on May 10th, 1788. And he was the second of four sons, so he had three brothers, one older, two younger, and he was born to a fairly successful and educated family, because his mother homeschooled him and all of his siblings. His father was an architect. His oldest brother was admitted to the Polytechnic School, or École Polytechnique, and became a lieutenant or lieutenant in the artillery before he was killed eventually. Rip. His younger brother followed in his footsteps himself and went into civil engineering, and he actually succeeded him eventually as a secretary in the Lighthouse Commission, which comes into play in the story later. And it also helped him, Augustine, edit his papers and works throughout his lives. And then finally, his youngest brother, the fourth brother, was a noted linguist, diplomat, and and he actually occasionally assisted him in negotiations. So a pretty educated family, and kind of like a close family, it seems, because him and his two brothers were always kind of helping each other throughout their lives. And additionally, one of his uncles was a paint artist who focused on the chemistry of painting, who became a professor at the Polytechnic University. And it was because of this connection to his uncle that he was actually later to collaborate with kind of the world's leading optical physicists during his day. So as a kid, Fresnel was considered kind of a slow child and not very good at memorizing things. So he struggled in school, and compared to his siblings, he was the slowest. And even at the age of 9, people still didn't consider him smart or anything like that. However, he had the ability, weirdly enough, to turn tree branches into toy bows and guns that worked far too well. So he kind of earned amongst some of his friends the kind of title of the man of genius as a kid, or the French translation of it at least. In late 1804, this is a while later after his childhood, he got accepted into the Polytechnic School, and placed 17th in its entrance examination. And this university slash school didn't start keeping records until 1808, so we don't know too much about his time there. Somehow we know that he didn't really make too many friends while he was there. However, in his first year, he took a prize for a solution to a geometry problem, which was posed by the famous mathematician Legendre. So, even though as a kid people didn't consider him smart, it turns out you don't need to memorize things to be smart. So he eventually graduated from there, and he enrolled in the National School of Bridges and Roads, which is where he became an engineer, and graduated in 1809. And he entered service as an ordinary engineer in training. And he remained under their employment in some form/way for the remainder of his life. So during Fresnel's time, optics was not this fully understood thing. I mean, it's still not perfectly fully understood, but back then it was significantly less understood. There were many different phenomena which cannot be described by geometric ray optics, so all these other theories had to be kind of proposed, and some of them worked in certain situations, some of them worked in others, but they didn't work in everything, and some of them disagreed with each other, and some scientists just straight up to believe some, even if they worked, because it turns out some scientists are very stubborn. So one example is Newton's corpuscular theory of light, which is kind of a predecessor to the quantized theory of light, which is photons. And then there's all these other theories, but I won't get into them. However, one of them was the wave theory of light, which was proposed by Christian Huygens, or I'm probably saying that wrong. Do you guys know how to pronounce that? Me either. Every time I say it differently. If someone knows how to pronounce it, message us on Instagram or email us. Tell me I'm doing it wrong. But Huygens proposed this wave theory in the 1600s, and not many people liked it. I don't know why, but there was not very many supporters of it. However, Thomas Young, which is another famous physicist, showed an important experimental result which agreed with this wave theory. And that was the double slit experiment, which we definitely need to talk about at some point because it's super important in physics. And this showed that light actually behaved as a wave and had interference effects. So light can interfere with itself, it can diffract, and all kinds of things. But Young was one of the only public defenders of this wave theory, and this was because of the ether problem. But that problem is, again, another topic which we've mentioned before, which was disproved. So he was one of the only public defenders until Fresnel came along. So, without going through all the details, basically Fresnel independently worked out his kind of own wave theory, which matched this previously proposed one, and with help from some other scientists, he came up with this convincing argument as to why wave theory is a correct theory and why it works. And this kind of was actually the first step in overturning Newton's corpuscular theory and supported Young's double slit experiment. And even by 1821, he was actually able to show via, physics and mathematical methods that his wave theory could actually describe polarization, where that was something that previously people couldn't quite understand. And he came to the conclusion that polarization is only possible if light is a wave and it's an entirely transverse wave. It has no longitudinal vibration whatsoever. So that'll mean something to the physicists out there. And finally, the lens. Where does the lens come in? So his brother worked at the Lighthouse Commission, and I think that's probably where this connection came from. There was a big problem in lighthouses at the time that if you want to produce a lens, like the lens in our eye we talked about, or the lens in your glasses, or a magnifying glass, if you want one for a lighthouse, it's this massive piece of glass. It's this enormous thing. It'd be super heavy. It's very expensive to make. How do you get it up there very easily? And another problem is that this piece of solid, huge glass, for a lighthouse, you want to take light from some source, say like a fire or something, and you want to project it out into the sea so people can see it far away through clouds, through fog, during the night, whatever, so that they can see the land and kind of not run into it, basically. One problem with having a solid piece of massive glass, or whatever material they use to make it, is that it absorbs a ton of the light that goes through it. So even if it focuses this light, the light that comes out is very weak. Much of it has been absorbed and doesn't transmit through. So this was a big open problem at the time. And Fresnel, probably because, again, of his brother, he came up with this way to create a very thin lens that focused the light very well, and this was the Fresnel lens. So it's this series of kind of steps. If you just Google Fresnel lens, you'll see what I mean. It's very cool looking. It's a series of steps in a circular shape, and it creates a very good focal point. It's very thin. It can even be as thin as a sheet, just a sheet of glass. It doesn't absorb much light at all, and it's a lot cheaper to make and easier to move around and whatnot. So he solved a bunch of different problems in one, and he wasn't the first person to come up with this idea, but he was kind of the first person to perfect it and commercially make it available. So this Fresnel lens was a very, very good invention, and it saved so many different lives during his time because of lighthouses, and it's been called the invention that saved 1,000,000 ships. And even today, Fresnel lenses are still used everywhere. They're used in traffic lights. They're used to correct several visual disorders, and I don't know the details of that, but I remember when I was younger, I saw some kind of specialized contact lens that was actually like a Fresnel lens, and I forget what the purpose of it was, but I think it helped for reading. Citation needed again. It's used in photography, and automobile headlights are actually Fresnel lenses, because if you think of it, it'd be kind of, it's better to have a small, thin sheet of some kind of glass or plastic or whatever inside your car to project your headlights instead of this big, thick one. Saves on material, saves on space, doesn't absorb light. They're used in image projectors, and they even have applications in solar power. So not only did these lenses save many ships, but they still probably save lives all the time in motor vehicles. You know, you're driving at night, you see something in the distance, you brake.
Yeah, I think to note a bit, because the Fresnel lens, well, you can notice it by the jaggedness of it. You think of lens as smooth curve, but to make it thinner, he basically figure out how to make like this really looking weird shaped jagged, like like a saw type of lens, and it works pretty well.
Yeah, it's very cool looking. It's like this kind of circular staircase of glass. I definitely recommend looking it up. It's very fun looking.
And if you have a VR headset, chances are that has a Fresnel lens as well, just so that they get that thin and lightness going on.
So that's kind of the basic story of Fresnel and how he helped change how we understand physics with his contributions to wave theory, and as well as his famous lens, which has saved millions of ships and probably more than millions of lives.
And with that, we will end our episode. Join us next week for what I believe will be our final episode of the season before we take a late summer break. But thank you everyone for joining us today. Feel free to reach out and contact us. And bye everyone.
Take care.
We'll see you later.